he needs specific help from the group, from all of us. He doesn't have ideas what the committee will be asking him tomorrow. And I know that right now it's a little too late to start serious preparation, but he needs some hints what could be the question and how to prepare to answering them. So if we can help him to orient his mind into this direction, he would appreciate it. Okay, so I suggest we will invest time in reading, and if you oh, hi Yvonne, nice seeing you. So I suggest we invest I don't know, maybe 15-20 minutes in reading Fatima's paper, share feedback after, and then Kevin will join and start his practice talk, if it is okay with you. Okay, then I will bring the manuscript and we'll try go over it, and when I'm done, I'll ask whoever is done first can speak up and induce discussion. I'll put my microphone off, so but as soon as I'm done, I will put it on back. Yvonne? And, did you went far enough in Fatima's work, or you need more time to more time? Okay, okay. Then, Aaron, do you need more time as well?
Couple of minutes.
Okay, okay, good. Yeah, then I'll continue reading a little bit more. Aaron, would you like to? I see that Kevin has connected, so we will finish discussing. Oh no, he's disconnected back. I'll send him. Oh, no, he's here. Kevin, we will finish discussing Fatima's paper, and then you will start your practice talk. Aaron, would you like to discuss, to give some comments or explain your comments?
I guess I just left a couple of comments on like Google Drive.
Okay, yes, it is. I'm sharing it right now, but are there any comments that you want to focus attention at?
Not really. It's just a couple of grammatical
Okay.
things that could be help the reader think less.
Okay. Yeah, thank you. Yulun, do you have some comments that you want to focus attention at? Okay, then I'll quickly go over a couple of comments. So I'm making comments in several places. I've started from conclusions, but I mentioned it also in results. The word delocalization sounds ambiguous here. Formally, the delocalization without any specifics means the wave function is homogeneously distributed over all space. But in this case, it is something more specific. It is takes specific shapes, and we may practice verbal explanation of these shapes. Fringes reflect wave nature of electron. This paper doesn't discover wave nature of electron, and it shouldn't sound this way. Maybe I understand it is a challenge, and I'm trying to verbalize it, but maybe it shows the degree of motion in this state. So the more motion, more quicker it changes in time, more dense fringes are. So we may try to update this verbal formula. Okay, for the introduction, I'm not sure if molybdenum silicide is so interesting two-dimensional material. To what I've seen before, it's typically molybdenum sulfide or molybdenum selenide. Eigenstates can be mentioned in the introduction. And for introduction, one may mention a little like maybe ARPS, angular resolved technique, and what is available theoretically general, not only brief general statement and goal of the paper, but a little overview what was done before in relevant areas. For the asymmetric, not clear. Probably maybe it means inhomogeneous, some more precise word. Delocalization should be defined here. The there is a very good statement that spatial distribution shows either localization near Dirac point or delocalization around, but it is not clear for reader what it depends on. So does it depend on index of orbital or energy of orbital? So nothing is wrong, but a little more specifics is needed because some readers read without looking at figures, and I know it is more kindergarten exercise to explain what I can see on a figure, but it's often helpful. Yeah, signature. How vivid the motion is depending on density. And this text in blue maybe can be expressed earlier at a point when one discusses choice of initial conditions. Okay, I think I'm done. I'll send this comments to Fatima. And Kevin, would you like to share your screen, or you would like me to just jump from between your slides when you are going through them?
I'll see if I can share my screen.
Okay.
Okay, is that my PowerPoint?
Yeah, I think we can see it.
All right. So yeah, I'll start my talk, and then if you guys have questions, feel free to interrupt me. All right. So yeah, everyone, please you know, if you have any questions, feel free to interrupt me. The more questions you ask me, the better prepared I'll be for my defense tomorrow. All right.
Just a second. Just a second. I believe if everyone except Kevin switch microphones off, the quality will be a little of voice will be better.
All right. Can I start?
Yes, please do.
Okay, so my name is Kevin Gima, and I'm studying excited state dynamics in one-dimensional thermoelectric materials. I'll wait a couple of seconds for it to change to the second slide. All right, I think it's gone to the second slide now. So, why is charge transfer important? Quick intro to charge transfer. You see this electron in the red atom over here excited by a photon. Then it gets enough energy to fill this electron hole right here. So then, essentially, charge transfer involves the movement of electrons. Charge transfer is important because semiconductors utilize this phenomenon. Charge transfer essentially increase the current. So anyway, and since semiconductors are used in everywhere from televisions to microwaves and every other technology, improving the rate or measure of charge transfer will improve the performance of everyday devices. All right, so that's why studying charge transfer is important, and also studying charge transfer also improves our understanding of non-adiabatic dynamics, which is essentially nuclear electronic interactions. All right, I'll wait a couple seconds for it to change to the other slide. Okay, so now photovoltaic process. Essentially, the sun is shining on a solar panel. So sunlight is emitting photons. These photons are exciting my electrons, and they're moving towards electron holes. So you have my n-type junction with electrons, and my p-type junction with the electron holes, and there's a junction between them two. So electron is moving towards the p-type to fill the electron holes. So this whole thing is moving electrons, so that's inducing a current, and this whole process is being used to power this light bulb. So essentially, the photovoltaic process is inducing charge transfer through the use of photons. Okay, so now for the thermoelectric effect. Here on the top, you have my heating. So this is my hot side. Then this is my cold side. On the left side is my n-type with electrons, p-type with electron holes. So what we're doing is we're inducing a temperature gradient between the hot side and the cold side. So what's happening is that some electrons over here with faster initial kinetic energies are going to travel over here to the other side, and then when they end up going together on one side, together they'll form an electrostatic field that's going to repel the electrons on the other side. So you have electrons here on one side and electrons here on the other side, and together they produce an electrostatic field. So there's a voltage between the two sides now, and that voltage can be used to induce a current. And you see this arrow here. You see that the n-type electrons are going towards the p-type holes due to this temperature gradient, and that's the thermoelectric effect. So the thermoelectric effect uses a temperature gradient to induce a current, in contrast to the photoelectric effect, which uses photons to induce a current. Okay, so lead Telluride nanowires. For what project is studying the lead Telluride nanowires? You might ask, why am I studying the lead Telluride nanowires as opposed to, thin films? Essentially because the nanowires electronic properties are easier to modify, monitor, and control. So especially in nanowires, it's easier to use temperature gradients, so it's easier to study the thermoelectric effect in nanowires than it is in thin films. They are widely researched by scientists and researchers due to their potential as a thermoelectric material. So for instance, the conventional band gap of a typical semiconductor is between 1 and 1.5 electron volts. And researchers have found that the lead Telluride band gap is 0.32 electron volts at 300 Kelvin. So that's really, really good compared to the conventional band gap I mentioned earlier. However, many challenges remain. Specifically, researchers are having some problems applying this technology to everyday appliances, and also in a regular unmodified lead Telluride nanowire, the charge transfer is negligible. So what scientists do is that they basically study doped lead Telluride nanowires. They basically dope these nanowires, and doping is essentially introducing an impurity into a material. So they might replace some of the atoms with iodine and sodium, which is what I'm studying. So um, scientists and researchers have found that when you dope lead telluride nanowires, they increase the charge or transfer rates. So one of the main goals of my project is to uh, confirm that, see if the doping process improves the charge transfer rates in my computational study. So a quick intro to the doping process. Here in panel A, you have your undoped nanowire, so the valence band and the conduction band and the valence band are untouched, they're unmodified. And then on panel B, you have the sodium doped. Here you see that electron is removed from the valence band. Panel C, you have your iodine dope, and you see here that the conduction band for your iodine is doped. All right. So, and then on panel D, we're proving the two types of doping together. So here, panel D applies to an excited state. So a photon excites on a sodium electron here in the valence band, and then the electron travels to fill the conduction band in the iodine. So the electron travels from sodium to iodine. It's important to note that panel D only happens in excited states. For ground states, the P and dope states exchange occupation. So just a quick note. Okay, so here we have a model of my dope nanowire. You see here that the unit cell length is around 110 angstroms. It has a cubic structure of approximately 300 atoms. The lead and telluride here exist in a 1-to-1 ratio. So here in the bottom equation, we see that lead has a 2 extra.
Kevin, may I interrupt and ask a quick question?
Yeah, go ahead.
You are showing in the lower left, you are showing that lead to Telluride distance is 0.009 angstrom. This cannot be true. Uh, it, it should be much less. It should be something like 2 angstroms. Please double check. If anyone cares, this interatomic distance, typical interatomic distance, is of the order of 2 angstrom. For these heavy elements, it could be maybe 2.5 or 3, but please double check. Okay, thank you.
All right, I will double check that. So lead has 2 electrons in its valence band, and telluride needs 2 electrons to complete its outer shell. So lead donates its 2 extra electrons to telluride, and together they form the compound lead telluride. So this is just for a regular lead telluride nanowire. So in my doped nanowire, we replaced 2 lead atoms with sodium, which you see here in the 2 blue dots. We replaced them because they're both N-type material, mainly because they're both donors. They both donate electrons. Lead donates 2 electrons. Sodium donates one electron. All right. And then the pink circles here are my iodine atoms. So we took 2 telluride atoms out and replaced them with iodine, and we did that because they're both N-type materials. They're both acceptors. So telluride accepts 2 electrons. Iodine accepts one electron. All right. So that's my doped nanowire in a nutshell. Okay, so before I get into the results, I need to tell you about the computational methods I use to calculate my expectation values. So first off, I have my density functional theory here. In regular quantum mechanics, we use the wave function. However, density functional theory, which is what I use, uses the charge density, which is represented by this rho function here. And this rho is a superposition of all orbitals from the first one to the HOMO orbital. All right. So I use density functional theory and the charge density to find my energy and position expectation values. And then a quick note, I get the position of my ions from molecular dynamics or Newton's equations. Excuse me. All right. So let's go to the next slide, which is my non-adiabatic couplings or my non-adiabatic dynamics. Here I find how the rates, namely I find how my energy and position expectation values are changing with time. And then the next line here, I calculate my transition rates. So here on this line here, this is my transition rate. This is the rate at which my electron goes from occupied orbital I to unoccupied orbital J. And then this is analogous to Fermi's golden rule. This here is analogous to charge density here, and this here is the transition rate. So I just wanted to very quickly point out that. All right, and then next what we have here is my density matrix dynamics. So I am figuring out how my charge density here is changing with time. Right here, I have my commutator between my Hamiltonian and my charge density plus my charge density times this, and this is essentially just the Fourier transform of my transition rates. A quick thing to point out here. My charge density here is time dependent. The charge density I was talking about, mentioning earlier here in density functional theory, is time independent. So this is time independent. This is time dependent. And this is also an operator, okay? All right, so once I find my density matrix dynamics, then I use that to calculate each element of my density matrix, which is represented by this rho sub I here. So then I calculate my energy expectation values for my electron and my hole by basically adding all the probabilities of the energies for each orbital from 1 to LUMO, right? And then note if I sum up all my charge density elements here, they'll add up to 1, all right? And then once I have this, I calculate my rates of relaxation for my electron and my electron hole by just taking the derivative of this with respect to time. Even though this is technically correct, what MATLAB actually used to calculate my electron relaxation rates was this. This is essentially just the integral form of my differential equation right here, all right? Okay, so this equation right here is the band gap law. So The second main purpose of my study is to compute my electron relaxation rates and my electron hole relaxation rates, and to see how well they correlate with this band gap law right here. So this K value is the relaxation rates, A is just a constant, and then alpha is just 1 over the Boltzmann constant times temperature, and delta E is the energy difference between the initial and final states. Any questions so far?
Kevin, we are collecting questions and we'll ask at the end.
Okay.
Only most important questions will be in the interactive mode.
Okay. So the next slide here is my density of states for panel A, my undoped nanowire, and panel B, my doped nanowire. So in panel A, my band gap is 1 electron volt. In panel B, my band gap is 0.9 electron volt. So two quick things to point out here is that by doping, we have states A prime and A in the valence band and conduction band respectively. And then we have another state, C in the conduction band here that we didn't have in the undoped nanowire. So doping has introduced three new states near the band gap. And if you just qualitatively compare them, you'll see that the area for the valence band and conduction band, their area is greater than that of the undoped wire. So that means there's a greater number of states available for the electron, and that means charge transfer. The measure of charge transfer has substantially increased for my doped nanowire. All right, so the next slide here we have is are my orbitals. These are all the orbitals I've considered in my study. So one quick thing to know is where my orbitals are localized on. So all my purple orbitals, which are my HO orbitals, they're localized near the sodium, as you can see. And then my LU orbitals, which are my orange orbitals, they're all localized near the iodine. All right, so just wanted to make a quick note of that. And then here we have my absorption spectra for the undoped nanowire, panel A, and the doped nanowire, panel B. So if you look on both, both one prime and 1 are dark transitions. So the number 1 here corresponds to the transition between A prime and A on my earlier density of states, and that's congruent with our expectations. We expect it to be dark because all the orbitals are localized near those states A prime and A. And then here's how my cone-sham orbital energies change with time. So at time 0, we initially see that our band gap is around 1 electron volt, and then as time goes by, we see that band gap essentially decreases to 0. So this band gap essentially disappears. All right, and then here are my ref field tensors that I calculated from my transition rates equation for the methods section earlier, if you remember. So I calculated ref field tensors for all 5 of the temperatures that I studied. So if you look at it, initial temperatures, you'll see that the transition rates are essentially negligible. But however, as the temperature goes up higher, we see that the transition rates start to substantially increase. Another thing to note is that states need the band gap initially, for instance, at the 300K temperature, are very close to zero. You can somewhat see that here in the 500, but then as at higher temperatures, states near the band gap have a substantial increase in its transition rate. All right, and then next here is my graph. I'm seeing how my probability density is changing with energy and atomic distance. So you can see here that the probability density is highest in my conduction band, which is in the upper corner right here. If you can see where my mouse is. All right. Okay. So in these results, I'm studying how my charge density changes with energy. Here at the 300 Kelvin temperatures, you see that there's hardly a change anywhere. But then at 500 Kelvin, 700, and higher temperatures, you see that relaxation occurs, and then essentially the higher the temperature, the quicker the relaxation goes. If you just take a quick qualitative examination of these graphs, that's essentially what happens. So just wanted to quickly point that out. And then here I'm studying how my position is changing with time. So there are two observations that I want to point out here. One is our charge transfer is localized near the iodine dopants, which are near the top right here. This is what we accept since uh, since iodine is p-type material, it's accepting electrons. It would make sense that all the charge transfer is localized near the iodine, and also at higher temperatures, the magnitude of the charge transfer increases. All right, and then next we have my electronic relaxation rates and energy. So I'm studying to see how my relaxation rates change with energy. And I'm also seeing how well they correlate with the band gap law. So, so for my electron relaxation rates, I can see that there's a moderate correlation here with the band gap law, as my R squared values demonstrate. And then for my whole relaxation rates on panel B, I can see that there's a little to no correlation with the band gap law. All right. One final observation to point out is that essentially the higher the temperatures, the higher the relaxation rates. So from here you can see that my relaxation rates are directly proportional to the temperature. You can see that in panel A and in panel B. So just wanted to quickly point that out. Okay, here are my relaxation rates, and here we're studying how they increase with temperature. So in panels A and B, we can essentially see that the graphs essentially overlap each other. They're on top of each other. And what that means is that the rate of change for the relaxation rates with respect to temperature is independent of the orbital transition. So no matter what orbital transition you're studying, the rate of change for that relaxation rate with respect to the temperature is going to be the same for all of the transitions. And up here you can see my rate equations. I'm essentially fitting my graphs to the second rate equation right here. And as you can see, there's a high correlation there.
Kevin?
So, what can we conclude?
Kevin, can I ask a quick question before you go to conclusions?
Sure.
So, can you go back one slide? Yes, this slide. So I know that there is almost no time to make changes, but if you will find like 20 minutes in your schedule, look here. You are showing in second equation logarithm of rate equals minus delta E divided by temperature. Well, with Boltzmann constant. So would it be possible to fabricate a third version of this figure where x-axis is not temperature but 1 divided by temperature? So I'm not Kevin, I'm not requesting to do it, but you consider if it will be useful, because it is often used in chemistry for so-called Arrhenius law. Because if your x argument will be 1 over temperature, then your dependence will look absolutely linear.
All right.
Okay? So just make, and I'm done. Please continue further with to your conclusions.
So we can conclude that doping improves the nanowires charge transfer, and that the band gap is inversely proportional to the temperature, as the last slide demonstrates. One thing researchers should do in the future is that they should look at transitions between orbital superpositions. And if researchers study this in detail in the future, they will find that orbital localization doesn't happen here. So in my study, we see that all the HO orbitals are localized near sodium, and all the LU orbitals are localized near iodine. If we're studying orbital superpositions, that most likely will not happen. All right. And then we find out that the band gap law only applies to electrons at higher temperatures. There seems to be a limited applicability to electron holes. And then my electron and my electron hole relaxation rates change at the same temperature rate, independent of orbital transition. So no matter what orbital transition you're looking at, the rate of change of my relaxation rate with respect to temperature is the same for all transitions. So a quick note before I close. This will have a great impact on industry. There'll be a quick computation of relaxation rates. So presently, researchers have to do long experiments to find the material's relaxation rates. However, if I and other researchers can show that the relaxation rates have even a moderate correlation with the band gap law, then researchers don't have to do these experiments, and there will be a lot of time saved in experimentation. And that concludes my talk. Thank you.
Okay, yeah, thank you, Kevin. So let me suggest that I'll probably bring the comments to the screen.
How do I move comments to change?
So Fatima, so would you like to, Fatima? Would you like to verbalize your comments? Maybe not everyone, but those that are mostly important.
I have one question that your thesis title is Excited Dynamics in One-Dimensional Thermoelectric Materials. So how the states are excited? It's by heat or like your title is Excited State Dynamics in one-D thermoelectric materials, and then right next slide you are talking about gas transfer and photovoltaics. But and in the whole talk, I don't know if anyone else has same thing, but I realized that it's not clear how the states are excited. So. Well, I understand that electrons are excited somehow, and then they will, went to the higher state, and then they are relaxing to the ground state. But how this electrons are excited?
Kevin, would you like to answer? I do not. I do. Or you are recording the. Or you're recording the question. Okay, let me try answering Fatima's question about Kevin's work. But Kevin, tomorrow you will need to answer it yourself. Description, computational description of thermoelectrics is quite challenging, and the description of the mechanism of excitation is more complicated than photoexcitation. So there are some analogies between photoexcitation and thermal excitation, but in spite of this, and well, there are different things and similar things. Because there are similar things in this work, Kevin does only treatment that is applicable to photoexcitation. And then there is a hope to utilize general trends obtained through photoexcitation to thermal excitations. Does it make sense? It is not ideal.
Yeah.
Yes, it is not ideal, but it is how things are arranged by today. The main approximation in our approach that we excite only one electron hole pair. One electron is promoted from one orbital to another one. In thermal excitations, there is simultaneous promotion from many occupied orbitals to many unoccupied orbitals. So one would need to change several things in the computational treatment.
But how it happens? Like it's a doping or what?
No. If one places electronic system with small gap on a thermostat,
Okay.
then
I see.
there are promotion of electron from occupied to unoccupied by a photon instead of a phonon.
So there is thermostat then.
Yes.
So it needs to be mentioned explicitly and how the states are excited.
It would be good. It would be good, and I believe that if you look on a slide number 3, Kevin does
Heating.
heat input. So heat input means thermostat.
Yep. Okay.
Does it answer your question?
Yes.
Okay.
That's what I wanted to know. Like a thermostat is a good.
Okay, thermostat is a good word. Okay, would you like to continue? Aaron and Yulun, if you would like to ask questions immediately as we go through slides, you are welcome to contribute. If you want, we can go through all questions by Fatima and then ask other group members to provide more questions. So Fatima, please keep going.
Okay. I need to open.
So you're asking why my Dove nanowire?
Yes.
Well, one can, I believe, can remove the word my.
Okay.
Okay, let's go further.
So why the temperature is 1000 Kelvin? Why not like 800 Kelvins or 1200 Kelvin? Why this particular temperature? Is there any reason?
Which slide are you referring to?
Kevin, would you are you answering to Fatima's question, or you want to give me to permit me to answer?
I'll try and answer it first.
I cannot see the slide number here. It's on the Eponcham orbitals.
Which side? Which side should I go?
KSO energy versus time graph.
Oh, okay.
So you're asking why I'm taking the energy of quantum orbital as a function of time at such a high temperature?
No, my question is why 1000 Kelvin? Why not less than that or greater than this? How did you decide 1000?
A measure of time. I've only had time to take this group result, mainly this energy at 1000 Kelvin, but if time permitted me, if I had more time, I would definitely see how this energy changes with time at other temperatures too. So at 300, 500, 700, not at 900. So I would definitely graph very, very specific.
So it was one answer that one can systematically scan different temperatures. I want to offer another answer to a question by Fatima. So in the slide number 5, there is an explanation. The temperature, Boltzmann constant time temperature, so that this thermal quantum will be bigger or equal than the gap. So what should be, which temperature should one heat the system so that KT will be bigger than the gap. And it will be of the order, I think, of the order of 3000 Kelvin. So then with guarantee, quantum electron will be promoted from HOMO to LUMO with 100% efficiency. If you take a little smaller values, maybe like 1000, then it will be smaller percent, but it will be noticeable percent in the distribution that thermal phonon promotes electron from HOMO to LUMO. So the range of temperatures for this exploration is determined by the value of the band gap. If the gap will be smaller, if Kevin would explore material with smaller gaps, probably he would look at smaller values of temperature. But in order to help electron to overcome the gap, one needs to heat the system to rather high temperatures. Does it sound logical?
Yes, so I think I'm good now. So other questions, I have some other questions, minor questions.
Okay. Which region of sodium, which is for hydrogen? Slides and give your comments. Do you have something to focus attention at, to highlight?
Yeah, I have a couple of things that I would say. So, like on your very first slide, when you talk about charge transfer, as an example, you give an example of a radio or a photon to do charge transfer. And I don't know, I'd be like 99% sure Stellana would ask a question about that. I've heard her talk about, because she'll probably ask something along the lines of charge transfer events are usually dark, or they have a very low probability of happening. So she'll probably want you to defend this argument.
So, Aaron, what is your suggestion? To remove this figure completely?
Yeah, I guess to avoid provoking questions, because I'm sure you talk about charge transfer and PN junctions, you'll raise some questions from him too. So you can talk about the use of PN junctions in these materials, but focus less on charge transfer.
So should I
say that again?
Should I take this slide out completely?
Not the slide, only the figure with red and blue balls. Right?
Right, so should I replace it with another figure, or should I just go leave it blank?
I don't know. We can type suggestions in this Google Drive document, but I also thought that definition of this blue and red circles is not quite clear. So maybe removing this figure, keep the slide, but removing figure is not a bad idea. You can think twice, but it may induce provocative questions. Okay, Aaron, please.
Yeah, I can remove the then.
Okay.
Just to confirm, I always keep confirming this, but this whole talk will be on YouTube, right?
Please repeat.
Will this whole talk be on YouTube?
I didn't understand. I didn't.
Will this whole talk be on YouTube?
Oh yes, yes. I am making an attempt to record everything we do right now.
All right, thanks.
Aspects you want to focus?
I guess a couple of other general questions you might get is that, well, you were in solid state in Andre's class, so he might ask about something about donor acceptor levels since you're dealing with dopants.
Okay.
And then since you're dealing with like a PN junction, Eric might ask something about whether you observe a depletion zone. Because that's like a textbook characteristic for the PN junction. So that might be something to prepare an answer for.
So so I need to fucking up on that. So I'm assuming this is this in a textbook or you are able to talk about this?
Please repeat the question.
So this the depletion zone concept. So is this in a textbook or is this in a paper that I can brush up on?
It was partially covered by Nathan Walker in his MS defense on Friday. And he was providing references. Ask me in the email if you want to develop further on this.
All right, understood.
Okay. Aaron, do you have more questions for highlighting?
I think the only other comment I would make is that for the least amount of work and to get like the greatest benefit, I think you could keep most of your introduction, but just rearrange it a little bit.
How do I rearrange it?
I guess I took some notes and giving you some ideas like how to rearrange it, but usually for like an introduction to a topic, like the general concept is to start broad and then narrow down to like the main question that you're trying to answer. So since we're dealing with thermoelectric, and you provide an example of photovoltaics, so you can start something along the lines of the high demand. And then you can do the fact, or then you could say that a lot of these are based on PN junctions and how to make those in materials. And then you can give an example of a familiar PN junction material like a solar cell that's established. And then transition to your novel research of using nanowires for thermal electrics.
So if I'm understanding you right, I first give general examples about thermoelectric materials, and then after that I transition into my main topic.
Mm-hmm. Because the way you have it arranged right now, it's like you immediately jump into charge transfer, and then you start talking about devices.
All right, let's take that into consideration. All right, so another question then. So you said that Svetlana might, oh no, I mean Eric, you might ask me about the depletion levels, right? For PN junctions. And then you mentioned another topic before that that someone else might ask me about. Can you remind me what that is?
Hear me or no?
Sorry, I actually need you. Can you repeat that?
Since you were in Andre's solid state physics, and he went over some examples, or he spent, I don't know, a week or two on doping, he might ask some questions that were covered in his class.
All right.
So something about doping levels, which you talked about in your slides, but you don't explicitly say.
I mean, take a look at his solid state. Any other suggestions?
Well, the one last one I have. So if you go to your band diagram, for that explains the doping. Like bands side by side. That kind of implies that you have two nanowires.
So I just take out panel C and C just for avoiding confusion and just have panels A and B there.
But I think what you could do is you could just you can't see where I'm playing. So you could put dopant levels just in one band diagram. So you could remove like the right half and then move your iodide dopant levels to the left.
I respectfully disagree. It's a decision of Kevin, but in this format, it's maybe one can keep the same style of the figure, but accompany it with more explanation. So panel A is the energy diagram of one nanowire which has no doping. Panel B shows energy structure of one nanowire that has only sodium doping. Panel C shows energy diagram of one nanowire which has only iodine doping. And panel D does show the co-doped nanowire which has both of the dopants, and the diagram has left and right sides because dopants form an interface, and electronic structure on the left and right parts of the model do not coincide. There is a dependence of electronic structure on spatial position. Aaron, would you accept if this figure is accompanied by such explanation.
Yeah.
Okay. Okay. Thank you. More comments from Aaron.
No.
Okay, thank you. Yulun, I have seen that you typed some questions in the chat line, but would you be interested to verbalize them and focus attention on any slides? Please, microphone.
Yeah, I guess my first question is more the introduction, because I think right now the introduction is too short, and I don't understand what is purpose of this study, and is there any similar work for this kind of material, and what kind of methods in the community is being used for this kind of study?
Kevin, would you like to give a quick answer?
Okay, so you're asking what the purpose of this study is. So the purpose of this study is to first and foremost see whether doping of that Telluride nanowire with iodine and sodium improves the measure of charge transfer. So that's the first purpose. And the second purpose is to see how well my electron relaxation rates and my electron hole relaxation rates, how well they correlate with the band gap law. So if I find that they correlate well with the band gap law, then researchers don't have to carry out long experiments to find the relaxation rates. They can just simply so that's the purpose of it. So
Okay.
besides, I want to add that the long-term purpose of the study is to see how my dope blood Telluride nanowire would work as a thermoelectric material. But since the time for this study is short, it's very difficult to obtain more findings that will help me conclude whether or not this would be an ideal thermoelectric material. In order to do that, I would have to obtain more data for different configurations, like maybe get some data for interface 111 and other configurations. So this is just one small piece and a larger question to see whether these nanowires would be good thermoelectric materials. Is that an adequate answer? Or no?
Sort of, I guess. But so what kind of methods are they used in the community? What makes your study unique?
Can you step in and think about this?
Kevin, would you like to answer, or you want me to try?
I'll attempt to answer, and then you can correct me.
Okay.
Just give me a couple of seconds. Okay. So as far as I am aware of, this is the first study that uses non-adiabatic dynamics to study charge transfer and iodine and sodium doped lead Telluride. So non-adiabatic dynamics, which is the study of how my computer and electronics interact together. That's what makes this study really unique because thousands of people know that these functional theory, but very few people in the world know how to compute non-adiabatic dynamics. So that's what makes this study. So that's the internet channel. If I made a mistake.
So I would add to answer by Kevin that in the community of researchers focused on thermoelectric materials, there is a standard approach of exploring electronic structure, static electronic structure of the materials, and the simultaneous co-doping and dynamics of charge transfer indeed was not yet brought into this community. So Kevin is trying to bridge two communities by porting, by moving the techniques that were used in photo-induced charge transfer in community into the community of thermoelectric materials.
Okay.
Are even other questions you want to focus attention?
Yes, I guess another question is about energy gap law. So I guess my question is, why is the energy gap law is so important?
Why is the energy what?
Why is the energy gap law is so important?
Oh, why is the band gap law so important?
Yes.
Okay, so the band gap law is important because if me and other researchers can show that there's high or even moderate correlation between the band gap law and the relaxation rates, researchers and then can kind of abuse relaxation rates faster with the band gap law. But however, if there's a little bit more correlation between the band gap law and the relaxation rates, then researchers would have to spend a long time to experiments to try and find what the band gap law is.
Yvonne, does it sound adequate to you?
Not really. I guess, so if this energy gap law is so important, then I guess it should be, like majority of your data should follow this energy gap law, right? But actually your results is quite different. So does it mean your results is inaccurate?
Well, yeah, Kevin, please try.
Okay, but not necessarily. I mean, what the data I have in this study is only an initial data. There should be a lot more data. Not just for just nanowires, but for nanowires of different configurations of different dopings of different interfaces in order to see if there's any correlation between the band gap law and the relaxation rate. Hold on. I want to try to answer your previous question as to why the band gap law is important. I'm going to take another crack at this. So the band gap law is important because it shows a direct relationship between the relaxation rates and demand for energy. And it also shows a direct relationship between the relaxation rates and temperature. So it provides such a clear-cut relationship between those two variables. And if the band gap law is proven to be incorrect, then that means the the relationship between those variables that I and discussed earlier is no. And yeah, that's all I got.
Even does it bring more sense?
I guess a little bit.
Okay, I can add, but basically repeat some of the statements from Kevin. So, in this interesting and challenging task to describe important process of charge transfer in these materials, it would be great to identify general trends for relaxation of excitation and general trends for charge transfer as function of different parameters. And before calculations were started, there was a hypothetical statement that maybe any data that will be computed in this work would approximately fit a general trend introduced by energy gap law. And in some sense, this work was formulated as to prove this hypothesis right or wrong. Does it make some sense?
But if we just look at the final results either confirm or deny the energy gap law, right? Then what's the point of this?
Well, even if gap law is denied in some circumstances, it is still a positive knowledge. It is a regular scientific procedure when one strategically sets up a goal, makes an effort to reach it, to prove this right or wrong, and then reports, so that if gap law would be 100% correct here, it would be a positive result. If it is not always correct or always incorrect, it is another result that will help researchers who will continue this direction of studying these materials.
Okay. Mm-hmm.
So it is not industrial or applied research. It's more fundamental research of exploring some concepts.
Mm-hmm. Okay. I have another comment about the green figure and the blue figures. So I guess the question is, why you show so many panels if they are basically the same? What's the point of doing that? Why not just focus on one panel and then just try to explain everything?
I want to show that the trends I'm pointing out with this figure are consistent for each orbital transition I've studied. So I want to show that it's not just limited to, for instance, the first row or that first transition, that it's applicable to the other three transitions as well.
Okay, then how about just 4 panels? Why you need to focus on different transitions?
I guess I'm focusing on these different transitions.
I guess my point is there are too many panels, and it is impossible for readers to just get enough information.
Can I contribute to the discussion?
Yes.
So I interpret suggestion of Yvonne in the following sense. Before your present slide with green figures, you may add another slide where you show only one green figure expanded over the whole slide. And then you explain in all details what this figure represents. Then, after exploring overall structure of this green figure, you can show your present slide with this 5 by 20 panels and see that and brag, tell like, I was exploring many different initial conditions at different temperatures. But showing one panel expanded to the whole screen would be, of course, much easier for readers and for the audience to understand. The same for the blue figures. If you make one more slide where you show case study, one example of one blue figure, and explain its structure, then you can go to your multi-panel figure and hope that audience will understand it. Yulun, would you accept such plan as response to your comment?
Yes, totally.
Okay. Kevin, would it make sense for you?
Yeah.
Yes?
Yes.
Good. Yulun, do you have more comments?
Yes, I guess my final comment is about the equations. So I guess, so first, right now there are no reference. I guess we need to just insert a reference. I guess you need to be prepared to explain every single term in these equations.
Can I put the references in another slide after the equations?
No. The tradition for the scientific presentations is to put references at the bottom of each slide. And typically one places maybe one reference at the bottom of each slide. It's not a iron strong rule, but if you would split equations and slides on equations and references on different slides, it will be not possible to follow. It should be merged together.
So equations from the same reference on the same slide.
Mm-hmm.
All right. Okay, got it. So I put the equation on the slide and then the reference on the bottom right-hand corner. Okay.
Even I apologize if I interrupted in the middle. Do you have continuation of your question?
Not really.
Okay.
Right. So maybe with this method session, maybe I should try to explain each term of my equations and then see if I understand everything correctly.
Kevin, there is a possibility that you make additional slide with explanation of each term of this equation and put it after the conclusions, just in case if committee or audience will start asking you questions, what each symbol means, then you go there.
All right.
this would be a practical solution. Okay. Let me show some comments. I'll quickly go over the slides. Yeah, we already agreed to remove this figure. I was asking what is the meaning of circles. Here we already discussed it with Fatima that band gap of lead telluride is a critical parameter that determines regime of temperatures for this application. For band diagram, maybe one can put a title. For the atomic structure, I think the interatomic distance is like 3.25 approximately between lead and telluride. You can double check it by measuring it in the JMO. Newton's equation from capital. There is a question about lowercase and uppercase energy. If time doesn't allow, keep it as is, but if time does allow, there is an explanation why we used lowercase epsilon and uppercase e. So when you multiply energy of Kohn-Sham orbitals, which have dimensions of electron volt, by dimensionless density, we get energy which has dimension. It is measured in the electron volts. But in the next two equations, we need dimensionless energy. So to have rate 1 over second or 1 over picosecond. So we need to convert energy with dimensions into energy without dimensions. Okay. And there is a trick to do it. So I'm attracting your attention to the top of this slide. So if you take this energy with dimension at time t, and then divide it by some reference energy, for example, energy at time 0 minus energy of time infinity, then the result will be dimensionless. If you have both numerator and denominator without of the same dimension, then the result of the fraction will be dimensionless. And the dimension full energy is changing in a range from value of energy at initial time t equals 0 to value of energy at final time t equals infinity. While dimensionless energy changes from 1 to 0. And then it is very easy to process it mathematically. If you process dimensionless energy, the dimensionality of the rate will be 1 over second or 1 over picosecond. Does it make sense?
Yes, so should I put it on this slide or in the slide after conclusions?
It is your choice. Just be ready to address this question if someone asks. I was putting it into the slides when I was presenting, but it is your free choice. If you know how to explain it, you can put it after conclusions or just verbalize it or write on a chalkboard or whatever. Just think about it and prepare. Okay, let me go further. I think you do not show equation how one computes absorption spectra. Committee members or audience may decide to ask it. We were discussing that it would be really great if you put an image of the movie of molecular dynamics. Do you still plan to do it?
If you have some time after the meeting, could you quickly show me how to do it?
So you do not remember how to do it from the class?
No, I don't remember.
Okay, please send me an email reminder, and I'll do it. I'll show you.
Okay.
Also, Kwon and Sham, those are family names. I would put them from upper cases.
Right.
Here is the answer on the question of Fatima. You may put labels on the here. Where is iodine? Where is sodium? For this suspicion about error, it's good if you realize and recognize it, but do not highlight it. It's only if someone will ask you, do you see any potential problems that you want to improve? But do not brag with potential problems right away. Also, you are showing equations for green figures, but you are not showing the equations for blue figures. I don't care because I saw these equations myself, but some of the committee members may request you to show or explain how this solid line and dashed lines were computed. So look into your thesis or papers from our group. Just meditate about it. Be ready to answer where these lines are coming from.
Okay.
If you need quick answer, it will be the same thing as for energy, but instead like density is multiplied not by energy, but instead you put the position. So
okay.
Position. Okay. I would put a little arrow to show that as temperature increases, dataset move up. And if you have time, making a duplicate of this figure where the x argument will be 1 over temperature would be really cool. And then, although most of your committee members are from physics, if anyone in the audience will be from chemistry background, it will be much appreciated. It is a standard so-called Arrhenius plot, like rate of reaction over inverse temperature. Okay, I'm done.
One question: can you go to the very last slide in my seminar?
Yes, I can.
So that slide with the extra densities.
I like it very much. It is a great slide, and you did a perfect job. It will. There is a very high chance that it will help you.
So, is there anything that's incorrect?
I do not see any glowing errors. Well, of course, Fermi is a person. One can put it with uppercase. But I think it is good. It is good. I like it.
Okay. One last question. Can you go back to slide 8? Okay, so I showed these equations, and you said I have to be prepared to explain each term. So could I explain each term in 1 or 2 minutes, and then you can tell me if I'm correct or incorrect?
You can try, but it will be quite a long exercise. Do group members agree to listen to this exercise? Anyone protests against it? I know that some of the group members do have appointments at literally 6:30. So if anyone needs to leave, I'm fine with it. So formally, let me announce the completion of the meeting, and I'll stay to listen how Kevin practices explanation of each term in the equation. But please do not miss your appointments that you may have set up long time ago. Okay, Kevin, go ahead if you want.
Okay, so I'll go as quick as I can. So first term is density functional theory. So this negative h bar squared over 2m times the gradient squared, that's of course the kinetic energies. This piece of rho comma r, that's the potential, but that's dependent on rho, which is our charge density, and charge density is the number of electrons per volume in this case. And then psi is of course our wave functions. And then in the next line we have rho sub bar. So we're summing from I equals 1 to HOMO. So we're multiplying each wave function by its complex conjugate. So that means we're taking the magnitude of the wave function squared, and that's essentially probability density. So like I said before, that's the charge density, that's the number of electrons per volume in this case. And then the position of ions lying is self-explanatory. Then we have our non-adiabatic couplings. So this is the expectation value for the rate of prime. This essentially measures how an expectation value changes when you're going from orbital I to orbital J, which is an occupied to unoccupied orbital. And note that both of these wave functions depend on little r, which is the position of the electron, and big R, which is the position of each ion. And the position of each ion is dependent on time. And next line we have the transition rates, which is the rate of that you're going from orbital I to orbital J. You can see here it's just one big integral.
Kevin, can I interrupt?
Yeah.
So this is the symbol M capital is autocorrelation function.
Okay.
Autocorrelation function of the non-adiabatic coupling, and so it is related to transition rate, but I would say it more gentle. So this autocorrelation function includes interaction term in the second order, and therefore it is related to Fermi golden rule. But I would probably consider to move your last line into space between your autocorrelation function and Fermi's golden rule.
Okay.
And then if one goes from time domain into frequency domain by Fourier transform, then this symbol M converts into symbol R, and it becomes to serve a role of transitions from different orbitals.
All right. And then I explained this commutator, which is my commutator between my Hamiltonian and my time dependent charge density. Right. So that's it, essentially all that is. Do I have to go into more detail about that commutator or no?
No, I don't. But I do want to hear more why you're in your autocorrelation, why you have this autocorrelation function, why the interaction between electronic and nuclear degrees of freedom is entering in the second power, is coming into the second power. Why there are no terms for the fourth power or third power?
For Fermi, what line are you talking about?
I'm talking for the symbol M M capital, autocorrelation function.
So why there's no like third or fourth power there? Okay, I'm not completely sure, but is it, I don't know, due to the Taylor series?
Perturbation theories, yes. Typically, if the lower order correction is, if the small first order correction is small, then any higher orders will be like smaller and smaller. Same like if 0.1 into second power will be always smaller than 0.1 in the first power. So higher orders will be always vanishing. And also you do not need to speak it out, but please be ready to interpret your non-adiabatic coupling as electron-phonon interaction.
Okay.
As a perturbation that phonon interaction imposes on electronic transitions. You do not need to say it, but if someone asks you to interpret what is the physical meaning of this term, you can tell that it is one of the implementations of the electron-phonon interaction, and physics audience will be happy about it.
All right.
Okay.
Next slide. Okay, so then the slide here is essentially computing my observable. So I'm computing my energy and experimentation values by multiplying the charge density for each orbital with my energy for each orbital, and then I'm just summing them across every orbital I have to find the most likely energy I'll get. So that's that first equation right there. And then on the next line, my relaxation rates are essentially how my energy expectation value change with time. And then essentially the third equation is just my second equation in integral form. That's all I can think to say about this.
Good. I'm glad with this. If I would be a picky committee member, I would ask you to derive the last equation, to show how one derives this equation. And it originates from assumption that dimensionless energy is equal to e to the minus rate times time. So if one integrates left and right part of this equation, integrate of energy dt from 0 to infinity on the left side, and on the right side one needs to integrate this simple exponential. So while you are integrating exponential, you need to change integration variable. So this minus k sub e comes outside of integral, and then here you put e to the power minus u times du, where u is this combined variable. And then if you perform this integration from 0 to infinity, at upper limit at infinity it will be 0, because exponential to minus exponential of exponential integral of exponential is exponential. At upper limit it will be 0, at lower limit it will be 1. And then you are obtaining the 1 over rate of transition is equal to integral. And if you need the rate of transition, it will be 1 divided by this integral, which is symbolized here by the power minus 1.
Okay.
Make sense?
Yeah, it makes sense.
Okay. I don't know if anyone will ask this question, but if you would have unlimited time, I would also prepare a slide with this little derivation. But it's up to you. There are too many things, and you decide strategically what is more important. Anything else for us to discuss right now?
I can't think of. One last thing. Can you go to the doping slide?
The schematic diagram, this one?
Okay, so you said for the ground state, the PN and then dope state exchange the occupation, right?
Yes. I'm going to introduce new empty slide and redraw this diagram over again. So for ground state and for excited state. So in the ground state, we do have occupation. Just a second. So in the ground state, we do have valence band completely occupied, and the dopant state originating from sodium is occupied, and dopant state originating from iodine is empty. But if one promotes system from ground to excited state, then the intrinsic valence band is occupied, and the electron from sodium orbital is moving to iodine orbital. And it creates inverse population. So HOMO is empty and LUMO is occupied.
Okay.
But if the system in ground state, then the sodium is filled and iodine is empty. So I wanted to highlight just this this fact.
All right. I think that's it for now. I'll send emails after this. So another thing, you told me to think about the questions about, like functionals and ask questions about functionals and whole singularities and other things like that. So can I send my answers to those questions and then you can check them in the morning? Or maybe tonight in the evening?
So you want me to answer right away, or you want to try and just check your answer with me?
I want to check my answer with you.
Okay, good.
All right. So will you be able to check on like in the morning at 7 9 or 10?
My schedule is quite relaxed in the morning. I'm checking emails around 7 a.m. Then I will be lightly busy maybe from 8 to 11. And then starting from 11, I'm free until your defense. But if early in the morning, I will first check emails and answer if anything needed.
All right, understood. So that's it for now. I guess I'll see you tomorrow.
Yes, so I plan to send you my comments and I will process recordings. It may take several hours, but approximately by midnight it should be ready.